All right, we're going to go ahead and get started. Hello, everyone, and welcome. Thank you for choosing to spend your valuable time with us. Today's webinar will cover post-quantum secure TLS 1.3 on application MPUs, presented by wolfSSL software engineer Anthony Hu, Crypto4A Technologies CTO Dr. Jim Goodman, and NXP Semiconductors principal cryptographer Dr. Joost Renez. We'd also like to give credit to S.J. Moon and Gareth Davies from NXP, who have been instrumental in this work. This effort is part of our joint collaboration in the National Cybersecurity Center of Excellence Project for Migration to Post-Quantum Cryptography. My name is Emma, and I will be moderating the webinar. All attendees will be in listen-only mode. If you have questions, please use the Q&A box. After the presentation, Anthony, Jim, and Joost will answer your questions. As always, our webinars are recorded and made available on our YouTube channel. If you'd like to stay updated with all the latest from wolfSSL, follow us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. Feel free to contact us via email at facts@wolfssl.com if you have any further questions. Before we dive into the technical presentation, I'd like to provide a brief overview of wolfSSL. Today, wolfSSL secures over 5 billion connections. We have more than 2,700 OEM customers and dozens of resellers. wolfSSL consists of over 50 dedicated employees, primarily engineers. This progress is of course supported by a strong partner network that we are very proud of. Since the beginning, our engineering team has developed several embedded security products, including WolfCrypt with DO178 support, a FIPS 140-3 certification and a FIPS-ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as WolfBoot, Java wrappers and JSSC support, and commercial support for curl, and our newest product offering, wolfHSM. These offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. Now I'd like to turn it over to Anthony, Jim, and Joost to discuss post-quantum secure TLS 1.3 on application MPUs.
Hi, this is Anthony. Yeah, my name's Anthony. I've worked with wolfSSL for a little bit more than 4 years now, and I'd like to go over the agenda of this presentation with you. So first, we're going to talk about wolfSSL, and sorry, Emma just spoke about wolfSSL, so we're going to talk a bit about our support for NXP parts. Then we're going to go into introductions of NXP and Crypto4A. Then we're going to talk a little bit about post-quantum algorithms and details of the IMX93. And then Jim is going to talk about HSMs and what they are and how they work. And then we're going to talk a bit about the summary of the upcoming proof of concept demo that we're going to be creating. And finally, a little explanation about certificate chains and how it's going to be constructed. Finally, we'll talk a little bit about the algorithms and that will be used and supported by the proof of concepts. Okay, so let's get into wolfSSL and our support for NXP parts. We've basically, through our support system and our own consulting, we know of that these particular NXP parts are supported by are used with wolfSSL. So we've seen customers using wolfSSL on these particular parts. Obviously, I'm not going to go through them, but all of them. But I will highlight the Freedom MCXN947. And the reason why is because I'll be doing an upcoming webinar, a joint webinar with NXP, where we show post-quantum algorithms running on that particular part. So that'll be really interesting. So what else do we support? Basically, the short answer is if it has an SDK with a C compiler, then we support it. All wolfSSL code is written in C89, and we're super platform independent. If you have a C compiler and you want a part supported, let us know. We'll just get it done for you. Okay, I'm going to hand it over to Joost, where he can talk about the he can give an introduction to NXP.
Thanks, Anthony. Yeah, so and I'm Joost. I'm in the Competence Center, Crypto and Security of NXP, where I'm a security architect, and I focus on a lot of the post-quantum algorithm migration topics that come up. So I think many of you will be familiar with NXP. We're a semiconductor company. We have a long history of creating hardware and also software. Also including the Motorola, Freescale, Philips. So a history of about 60 or more years. Today, we have about 33,000 people working for NXP, a lot of people working also on R&D. As I mentioned, myself, I'm in the crypto and security team, consisting of a few hundred people with a dedicated focus on security topics. And within that team, we even have, for now several years running, also post-quantum teams of maybe 5, 6, or even more, working on the upcoming topics for post-quantum algorithms. So NXP operates in many different applications domains, specifically, automotive, consumer space. For this talk, we're focusing mostly on our application processors in the edge or the industrial edge domain. If you could go to the next slide, Anthony. So these are our processors that support applications mainly for edge applications. So there are different ones, for example, the automotive edge applications, factory automation, so industrial automation, robotics, but also healthcare, building, home automation, and many use cases that involve some kind of edge computing, which is, of course, more and more these days. Yeah, next slide, please, Anthony.
Okay, so I guess we'll bring it over to Jim to talk about Crypto4A.
Yeah, thank you very much, Anthony. Hi, good morning, everybody. And now for something completely different, as opposed to NXP, which is a very large, well-known company, I'm going to try and give you some insights into who Crypto4A is. We are a much smaller company on the order of about 30 some employees, and we are a Canadian technology company that is basically developing the next generation of quantum-safe HSM technologies. And as I said, we're Canadian, so we're headquartered up in Ottawa, Canada. My name is Jim Goodman. I serve as the CTO of the company. I'm also one of the co-founders, along with 3 of my colleagues. And basically, our story is that the 4 of us all met back in the days of Chrysalis ITS, which, as you'll find out when we talk about HSMs, was one of the original inventors of the modern HSM, essentially. And what's even kind of interesting there is that the product we developed there, the Luna product line, is actually the foundation for what TLS sells now in their Luna product line, because over the years it had been acquired. That being said, we've been doing this for a very long period of time, and one of the things that's kind of funny is our customers always call us the guys with grit, gray hair, and a passion for security. And thanks to that grit and that passion, we've managed to develop and deploy the first and currently the only truly quantum-safe HSM that also is NIST certified to implement all of the currently standardized post-quantum cryptographic algorithms, which is something Joost and Anthony will describe to you in a bit. In addition, we also offer a fully functional software emulator of our platform, and that's going to allow you to do rapid prototyping of HSM applications without the need to go and procure a costly piece of hardware. Anthony, next slide, please. Excellent, thank you. So of course, if you do want to procure some of that costly hardware, we'd be happy to sell it to you. So basically what we do is, this is an idea of what our product offerings are. We offer high assurance hardware, and that comes in a variety of platforms based on either our QX Edge design, which is essentially a high assurance HSM element bundled with several configurable computing elements, and that all happens within the same security boundary. So you can actually implement really kind of complex, as well as reconfigurable kind of personalities to do complex business security flows. Alternatively, if you were looking for a more conventional approach, then what we offer is a network attached HSM in the form of our QX HSM blade form factor, and then that can be fitted into different types of chassis, be it a 1 blade chassis, a 3 blade chassis that fits into your standard 1U rack space, or even a high density 12 blade chassis that goes into a 4U space, which we would use for basically for data center and cloud kind of high density implementations and applications. That's it, Anthony. And that's Crypto4A.
Okay, so let's get back to Joost, and he can talk about post-quantum algorithms.
Yeah, thanks, Anthony. So again, I think many of you will be familiar with post-quantum crypto, so this is a relatively brief introduction. The context being that quantum computers are under serious development. We see a lot of headlines. We see a lot of funding now being given out on many different organizations, both in the EU and in China and the US. And the development and the sizes of these quantum computers kind of increasing very rapidly. And in this case, if you go to the next slide, maybe, Anthony. Yeah, thank you. So the risk here being that if a quantum computer is sufficiently large in the foreseeable future, and exactly when this will be remains unclear, but if we're looking, for example, at the EU post-quantum roadmap, referring to the recommendations from the BSI, who's closely tracking the development of quantum computers, their current conservative estimate is that by 2040, we'll have a quantum computer that is sufficiently large to threaten current classical algorithms. So if a quantum computer has a certain size that it's capable of running either Shor's algorithm or Grover's algorithm, they'll have two major implications. So the first one, being able to execute Shor's algorithm, means the mathematical hard problems underlying RSA and ECC are no longer hard, essentially meaning that all the cryptographic algorithms using or based on these problems, so any RSA, any ECC, any Diffie-Hellman type algorithms are completely broken and need to be replaced by alternatives. And it's these alternative algorithms that we refer to as post-quantum cryptographic algorithms. There is also an impact on the symmetric side. So by Grover's algorithm, there we have AES and SHA. They're not totally broken. Recommendations differ depending on who you talk to. But here, the conservative recommendation is typically to double your AES key sizes and to maybe increase your digest sizes if you want to be absolutely sure there is no impact of Grover's algorithm on your symmetric primitives. If you go to the next slide, please. Yeah, so there are several reasons why, even if 2040 sounds far away, that post-quantum crypto is already relevant today. So firstly, on the left here, we're already seeing standards being developed and also regulation coming out, again, coming from the US, the EU, and also China is now starting a post-quantum cryptographic standardization effort. Specific regulation is already setting relatively aggressive timelines for migrating certain use cases towards post-quantum alternatives. So looking at CNSA 2.0, they're mandating for any national security system in the US that firmware software signing should be included by 2027. If we look at NIST, they're disallowing RSA and ECC by 2035, so also implicating FIPS 140. And also the EU now has a very similar timelines and milestones mentioned in their tentative PQC roadmap, also mentioning firmware software signing and high-risk use cases such as harvest now, decrypt later, so very relevant for TLS, targeting by 2030. And there may be two concrete security use cases here. The first one, maybe the most relevant for this talk, is the store now, decrypt later type attacks. Even if a quantum computer is not here today, somebody that's able to intercept communication, let's say a TLS 1.3 encrypted session, if they're able to collect this and store it in storage for 10 years, 15 years, they might go back in time, or in 15 years, they might collect this piece of data, decrypt it, and recover whatever data was encrypted today. So it depends very much on the sensitivity of this data, if this use case is applicable to you or not, right? If it's some telemetry, maybe not. If it's personal data or government secrets, this is, of course, a very relevant type of attack. And the main reason why TLS 1.3 is already migrating towards post-quantum alternatives, and even many deployed systems are already including post-quantum secure versions of TLS 1.3. The second big use case is maybe more related to long lifetimes of devices. Many systems, especially at NXP, are in the field for 10 years, 15 years, 20 years. If you think about a car or many other systems, these lifetimes can be very long. So if there's any piece of hardware or any part of the system that serves as a root of trust, or that might be difficult to include, after deployment of the hardware, this should already be covered today. So this is typically what we refer to as crypto agility. We want to make sure that whatever post-quantum algorithms are supported in our hardware deployed today holds up for the next 15 years, and anything that is not yet post-quantum secure should have the possibility to be updated and be agile for changes in the post-quantum or in the cryptographic algorithm recommendations. You can go to the next slide, please, Anthony. So having a look at what's coming in the post-quantum domain. So there are many efforts to develop new standards. So starting from the left here, already in 2020, we had the hash-based signature schemes from NIST, so LMS and XMSS. Now, since summer last year, since summer 2024, we have the first set of NIST standards from the PQC competition. So we now have MLChem, which is MLChem, which is the main key exchange, also targeted for TLS 1.3. We have MLDSA, the most general purpose signature scheme, and also the recommended signature scheme from this side. And we have SLHDSA, which is an algorithm maybe more targeted towards firmware software signing. There's more to come. So NIST standardized also Falcon, FNDSA, and HQC. So HQC was standardized this year. I think the rough timeline from NIST is to have this standard also ready in 2 years or so. So when that happens, we'll have also an alternative key exchange algorithm for MLChem. There are others. Korea has an algorithm standardized in the KPQC competition. As I said, China is starting to ramp up on developing new standards. We also have in Europe ISO looking at alternative algorithms, for example, FrodoChem and Classic Macaleese, which are slightly more conservative options, but also much bigger. So for the embedded space that many of us operate in, they're maybe not as suitable as some of the initial NIST algorithms are. If you go to the next slide, please, Anthony. Yeah, maybe next one again. Yeah, so introducing a little bit our proof of concept, right? So our proof of concept is running on the NXP IMX9 series application processors. Like I said, these are part of our secure connected edge business line. So there are different variants of the IMX9 series. What we'll be running on in the POC is the IMX93. You see that in the bottom right in blue. So it's a relatively general purpose processor. Its main focus is cost sensitive applications for high performance and where many IOs are necessary. But I also wanted to highlight some of the next generation, so IMX94, 95 that are currently in pre-production. Again, from focusing, having a similar architecture, but focusing on slightly different application domains. So all of these processors, support multiple Cortex-A processors, that they support Linux. And if we look at the security storyline, if you go to the next slide, maybe Anthony. If we look at the security guarantees in this series, they all support what we call an EdgeLock Secure Enclave. So this is a dedicated security unit, which is really physically isolated from the application side. So there are multiple Cortex-A cores where application software will be running. The secure enclave is really physically isolated. It has its own core, so its own CPU, and it's really designed to offer strong security guarantees for the rest of the system. So it really acts as the root of trust for the system. It's capable of hosting keys, so it has a key store, so it can isolate keys from the application space. It really drives and monitors any integrity on the whole SoC, so use cases like secure boot, secure update, and they're really driven by the EdgeLock Secure Enclave, and this is supported in all of the IMX9 series. If you go to the next slide, maybe, Anthony. Thank you. So yeah, tying this all back to the POC and to PQC. So what we are doing in the POC is enabling post-quantum runtime support for the Secure Enclave on the IMX9 series. So what that means essentially is that there will be a crypto library running inside this enclave. So again, physically isolated from the rest of the application domain, which is able to host MLChem keys, it's able to host MLDSA keys, and to do an MLChem encapsulation, decapsulation operation, and also MLDSA signing and verification. And it's also able to execute a TLS 1.3 hybrid key schedule, meaning that any key material that is used as part of this TLS session does not have to leave the EdgeLock Secure Enclave at any point in time, again, offering very strong key isolation from the rest of the system. For next generation, so for IMX9.4 and 9.5, we're also adding very strong platform security. So 93 is an existing processor, so we don't have the opportunity to update the ROM or the hardware. For 9.4 and 9.5, which are upcoming, we also add a real post-quantum secure root of trust. So we have support for MLDSA 87 in ROM and in hardware. So this supports CNSA compliant secure boot, secure update, secure debug. It includes hybrid modes. It also includes SHA-3 hardware, helping with the performance for many of the post-quantum algorithms. And it even allows you to integrate your own key material inside the Secure Enclave to ensure also secure boot is fully covered for your applications as well. Next slide, please, Anthony. Yeah, so finally, some kind of initial performance numbers from the proof of concept. So like I said, we integrated ML, Chem, and MLDSA inside the crypto libraries inside the Secure Enclave. So this Secure Enclave is running at 200 megahertz. And here we're measuring the runtime of the post-quantum algorithms from the application core. So it's requesting, so it's generating a key, storing it in the enclave, and then requesting to do an encapsulation or decapsulation or key schedule. This interface towards the application is to make Anthony's life easier, is integrated into a kind of a C runtime library. So there are different ways in which this can be integrated. For the initial POC, we have an open source user application library that we're using, but this is also typically integrated into standard interfaces such as PKCS11 or others, Embed TLS or others, to make it easy to use also these hardware supported APIs. So looking at some of these performance numbers, right? So for MLChem 768, we're seeing keygen, encapsulate, and decapsulate hovering around the 15 milliseconds, again at 200 megahertz. We're also able to run the full hybrid TLS 1.3 key schedule. So this includes the hybrid decapsulation as well as the elliptic curve Diffie-Hellman operation. And so all of that combined currently executes in about 21.4 milliseconds. For MLDSA, as you can see, it's a little bit slower. That's expected by the design of the algorithm, in particular sign, which is typically the slowest part of the algorithm. So we're seeing maybe 45 milliseconds for keygen and verify, and the average signing time hovering currently around 180 milliseconds. As I said, future generations will have SHA-3 hardware included. So if you profile the runtime of these algorithms, you'll see that a lot of it is spent in the software SHA-3. And so we really expect a significant speed up by including SHA-3 hardware for also future platforms. Yeah, next slide, please, Anthony. Thank you.
Now we'll move on to Jim to talk about HSMs.
Yeah, thank you, Anthony. Excellent talk, Joost. And in fact, a lot of that kind of is relevant to what I'm about to discuss. So a hardware security module, or an HSM, is essentially it's a physical device that provides a high assurance generation, management, and use of cryptographic key material. In some respects, it's kind of like the EdgeLock Secure Enclave that Joost had described, but taken to another level, basically to up the assurance to provide additional securities. And this whole concept was originally developed back in the 70s by a gentleman named Mohammed Attallah, and he was designing the device at that time in order to support payment transactions for doing digital commerce and the likes. And they obviously needed a trusted element that they could use to process these payment transactions to provide the security they were after. Now, that being said, the modern incarnation of what you would think of as an HSM today, that kind of came online back in the mid to late 90s. And this was basically, it was in the interest of trying to facilitate online trust and identity, which was needed to support the digital commerce over the internet, which was just kind of coming into being at that point in time. In fact, if you take a look at essentially the digital economy, if you look at what that actually is composed of, well, you have this digital economy, and that economy in turn is based on the concept of having digital identities that can engage in digital commerce, essentially. And this can represent a person, an application, a physical device, whatever that may be. Now, those identities, in order to provide that identity, you have to rely upon the notion of digital trust. And that digital trust is going to be facilitated by the use of public key cryptography. And that in turn is going to utilize keys and certificates in order to establish something called a public key infrastructure. Basically, it's kind of like the web of trust that we use to establish identity and trust on the internet for the most part. That PKI in turn is going to rely on a root of trust. Joost had pointed it out in his previous thing in the next generation of the i9s. They're going to actually have an embedded root of trust for their devices. So we need to create those roots of trust. We need to insert them into devices. Well, those roots of trust have to come from somewhere. And furthermore, given that they are the root of trust, we probably better be very careful that we basically create and protect them in a very kind of careful way. And that's where you're going to find hardware security modules. They are the devices sitting at the bottom of this stack that allows the digital economy to work, essentially. And they are basically, like I said, they are essentially a high assurance device that allows you to create, manage, and process cryptographic keys and transactions. And the way you get that kind of high assurance as well, first off, you use very resilient physical security, and that means using active kind of tamper detection and response mechanisms. You also need to introduce robust authentication and control mechanisms in order to protect those keys in their usage so that anybody can't just come up and start using those keys. Lastly, you're going to want to take that design, and just because you think you've done it correctly, well, you're going to have to actually go out and you're going to have to get a third-party lab, which is certified by independent agencies, and they're going to basically assess your implementation. And they're going to run through a bunch of tests, and then they're going to submit that to some standardization body, which typically is going to be NIST in the case of using something like FIPS 140-3 certification, or the common criteria certifications that are used outside of North America as well. Now, adding to all of that, of course, is the notion that you also need to be, as we've kind of alluded to already, Joost had touched on some of the concepts, we need to be crypto agile in these designs, and we also need to be quantum safe. Next slide, Anthony, please. So let's kind of break those down. So when I talk about quantum safe or quantum safe HSMs, really this is built on the fact that an HSM is both the provider of cryptographic services, as in generating keys, signing things and likes. It's also a consumer of cryptography because in order to deliver those services, it needs to have a number of internal cryptographic services and a foundation of security upon which it's built. Okay? So if we want to make something that's quantum safe, then we need to ensure that we are using quantum safe cryptography, both providing it as a service to the customer, but internally for these kind of internal components and capabilities, we need to ensure that those are quantum safe as well. And that's where a lot of HSMs today run into trouble because a lot of them are using old classical cryptography internally. But basically, when I talk about what these internal things are, well, obviously you need roots of trust, and Joost had alluded to that in his previous slide. You also need to manage those roots of trust. You need to have a secure boot as well as a firmware update process that needs to be secured by quantum safe mechanisms. You need to be able to transfer information between HSMs. You want to protect those key transfers. You also want to be able to store material outside the boundary of the HSM. You want to do that using quantum safe techniques. And then lastly, you want to be able to do a test to certain capabilities and properties, and that should also be rooted in a root of trust that is quantum safe as well. So in order to be truly quantum safe, the PQC, post-quantum cryptography, needs to be leveraged in order to provide all of these kind of core capabilities. And that is what distinguishes a PQC capable HSM that can Duke PQC algorithms from a true quantum safe HSM, which not only can provide those capabilities, but is actually secured using post-quantum cryptography itself. Next slide, please. And then lastly, I'll touch on the concept. Joost had mentioned the notion of crypto agility, which is really, really important because as we're seeing, we're currently going through a complete transition. We're going from classical cryptography in all of our services to using these post-quantum techniques. But the journey doesn't stop there. We're going to continue going into the future. We might have new post-quantum algorithms. So what we need to do is we need to design elements and protocols in that can handle the notion that instead of having a fixed point in time, single-use cryptography, we want to have something that can evolve over time. So basically, given that the HSM is a foundational element in a security architecture, well, what does that mean? It needs to be responsive. It needs to be able to adapt and evolve over time. So when we're designing them, we need to ensure that the device can handle whatever's going to be thrown at it over time. So we have to devise solutions that are able to evolve over time and as well as maintain that backwards compatibility that Joost had mentioned, where you have things that are in service for 10 or 20 years. So to do that, we use crypto-agile kind of architectures. It's really just an agile architecture from the ground up. And what we're going to do is we're going to leverage kind of robust and secure quantum safe upgrade mechanisms to allow that architecture to evolve, combined with reprogrammable components such as FPGAs and the like, which allow us to create performance solutions across a wide variety of algorithms, including ones we haven't even seen yet. We want to have that flexibility to adapt and change over time. And then furthermore, we need to ensure that we're using APIs that are flexible enough to allow us to, again, to adapt over time as we get new protocols and new algorithms being put in front of us. And that's the basic overview of an HSM. Back to you, Anthony.
Excellent. So, yeah, this is Anthony again. I'm going to talk about this upcoming proof of concept demo that we're going to be doing. And so let's move on. Oh, before I do, going to bring back Joost, and he's going to talk a bit more about the IMX93's role in this.
Yeah, I think much of this we already covered, Anthony. I think this is just a kind of visual representation of how the secure enclave sits inside the IMX93. So again, like I mentioned, we have a kind of chain of trust where we have a hardware root of trust. As Jim also mentioned, this typically verifies an extended root of trust, which you can imagine is a piece of firmware that might include some additional algorithms or additional features that are not included in the hardware. And this then serves as a kind of chain of trust towards the application space where further software might be running and might be authenticated. So this is to indicate, again, the physical isolation between the secure enclave, which is really a dedicated security unit in the application domain, and also they're trying to control the authenticity and the integrity of the whole system, including also giving runtime support for post-quantum algorithms. Yeah, so again, this is and then to highlight where all the pieces sit, right, in the POC that we're building. So how does this connect together? So first, in the bottom and in red here, we have what Jim was talking about. So any assets that have to do with authentication, like any public keys or certificates, will have to be injected by a trusted HSM. That's the Crypto4A part of the story. Then NXP adds support for crypto libraries and firmware. So this is what I was mentioning before. We have support for MLChem, MLDSA, and also the hybrid TLS 1.3 key schedule. Again, trying to make this as easy as possible to access through the application domain with either open source interfaces or standard interfaces even. And then finally, Anthony is taking care of the TLS stack. So running the wolfSSL client on the application cores, so the Cortex-A cores, and interfacing them with a wolfSSL server, which can be either another IMX93 or it can be a laptop or something else that's running the wolfSSL server side. So again, also having support for a hybrid TLS 1.3, and really ensuring this kind of encrypted TLS 1.3 client server communication.
All right. I think it comes back to me now. And we're just going to look quickly at the architecture of this. Most people who are familiar with wolfSSL know that the build products include, obviously, the wolfSSL library, So usually that comes as on a POSIX system, it would come as a .so file or a .a file if you're statically linking. But also the build process also generates a lot of little sample applications or example apps. Those include a TLS client and a TLS server. And so that's what's going to be run as the application on both sides. So for example, on the left side, we have here that the IMX93 is going to be a TLS 1.3 client. And on the other side of it, it's just going to be a Linux x86 64, or even a Raspberry Pi, or just about any kind of device that we run on. But typically, for this demo, we're just going to use an x86 64. So yeah, that's just going to be a regular laptop. Um, and so what's going to happen is the Linux x86 64 machine will execute a server. That server will load up a server certificate as well as a server private key, which will identify itself, which will help identify itself to the client. Notably, the server certificate will have a um, an MLDSA public key, and the server private key will be an MLDSA private key. And that will obviously be calling down to wolfSSL, which takes care of the protocols implementation, and that will call down to wolfcrypt, which will take care of the algorithm implementation. That's on the server side. On the client side, it's very similar. There'll be a root CA certificate that will be loaded by the clients, and that will be used to verify the server certificate. And then wolfSSL will it will call down to wolfSSL for the protocol implementation. And I forgot to add wolfcrypt here, but there will be a wolfcrypt layer, and that will then call down to to the EdgeLock Enclave that Joost has been talking about. So it's really important to note that this effort all came together because Crypto4A, wolfSSL, and NXP are members of the NIST NCCOE project for migration to post-quantum cryptography. And yeah, and so we all met there and kind of got together and said, hey, wouldn't it be cool to kind of have this demo where all three of us can participate and bring some sort of bring our part to this demo and have an interesting little conversation about it. Okay, so we're going to talk a bit about the certificate chain, and we're going to bring back Jim to talk about this.
Yeah, thanks, Anthony. Yeah, so let's look at the certificate chain that we use in the proposed proof of concept. But before we do that, let's talk a bit about trust chains in general in embedded applications, which is quite interesting given the variety of elements and chains that may be required. Now, typically the first thing you think of when you think about kind of a trust chain is you think about some kind of hardware-based root of trust, which can be used to securely boot the device, and Joost had mentioned this before in his talk, as well as to validate any firmware update operations in order to ensure that any firmware running on the device or being downloaded to it are in fact valid and coming from a valid source. You might also need to inject key material into the device. Now, Joost had mentioned the notion of secure provisioning. So you may want to load keys into a device. So basically what you need to do there is you need to have the ability to create that kind of provisioning blob of information, generate those keys, and securely provide them into the device during the manufacturing process. And then lastly, you may require the inclusion of a more conventional kind of public key infrastructure-based certificate chain, which is what we're doing in this proof of concept. And basically what we do is we create those keys as well as the certificates, and we basically inject them during the provisioning process, and they provide the ability to have basically a digital identity of that device. Now, of course, embedded applications tend to be constrained, both in terms of the types of storage and the amount of it, as well as the amount of computing power they have to bring to bear on these sorts of problems. So basically, this kind of leads to some pretty cool trade-offs as we try and provide that trust within whatever the storage and computability envelope is of that device. One common trade-off that we use, and I think it had been alluded to previously, is the notion that instead of storing the full root of trust, which especially in the case of post-quantum algorithms could be quite large on the order of several kilobytes, instead of storing that, we would store just a hash of that key value. And then basically we'd provide the root of trust with the thing that's going to be validated. And then we could verify the root of trust against that stored hash. And then if it's valid, we then use it to basically process that trust chain. Alternatively, we could also then use a more kind of conventional PKI-based certificate chain. But if we do that, then typically when we're trying to minimize the size of that chain, because again, we need to store those certificates, and as well as we need to process all the certificates in the chain. So typically in an embedded application, we'll try to minimize that, try to keep it to a minimum, which is typically you'll have a root identity, and then that root will then be used to sign end entity elements or devices themselves, which is kind of cool. Now, similarly, when it comes time to actually talk about, once we've decided what that trust chain is going to look like, we have to talk about, well, how are we actually going to provision it onto the device? There we tend to have two different types of approaches. One, if it's a reasonably competent and capable embedded device, then that device can actually participate in the provisioning process where the device itself will generate keys. It will use those keys to generate certificate signing requests. It'll hand those off to the HSM element. The HSM will then sign it, and it'll basically return the certificates back to the device itself. And that's nice because now the key material never leaves the embedded device. But for some embedded devices, they simply don't have the capability to do that. So in that kind of case, you'll rely on the HSM itself to generate all the keying material, generate any certificates that are required, and then just return essentially a provisioning blob to the device itself. And that provisioning can be done either in a secure facility where we don't need to secure that kind of transfer between the HSM and the device, or we could do it on some kind of remote manufacturing case where you can set up a secure tunnel, and then you can basically push the provisioning blob through that tunnel and then have the device basically personalize itself on the manufacturing floor. Next slide, Anthony. Now, in this case, like I alluded to, though, we're going with kind of a straightforward kind of PKI-based certificate structure. So basically, in this case, we're trying to keep things as simple as possible. So we're just going to go with kind of a minimal two-level certificate hierarchy, like you see here. And basically, we're just going to have the HSM generate all of the keys and certificates, and then they're going to deliver those fully contained provisioning blobs to the device and the wolfSSL application. The chain itself consists of a root certifying authority certificate, which basically validates any end devices, which are the end entity certificates. Each of those represents a device, and in this case, that's going to be the I-93 device that's running the wolfSSL application. We've chosen to use a homogeneous certificate chain in which basically all steps in the chain use the same cryptographic algorithms. In this case, we're going to use MLDSA 87, and we're going to use the pure variant of it for any kind of key values as well as digital signatures. That root key pair itself is generated on a Crypto4A QX Edge device, which Anthony had mentioned, the NCCOE. We actually have a device installed in their lab, and we're using that device to do all of the key generation, as well as generating all of the subsequent certificates and the likes. So it's going to generate the self-signed root CA certificate. It's also going to generate the individual key pairs for the end devices, and we're going to generate that end-to-entity certificate from that as well. And then when that's all done, the HSM is going to bundle up that root certificate as well as the end-entity certificate as well as the device key pair, and it's going to create a provisioning blob, which we're then going to provide to the end device, and then wolfSSL will use that in order to establish the TLS 1.3 session. And that's it for the certificate structure. Back to you, Anthony.
Okay, so this is Anthony again. So most people who kind of become aware of post-quantum cryptography want to really know about, performance, and they want to know about, is it really going to affect, how are these algorithms going to affect the end user? And generally speaking, the performance of these algorithms is fine. There's no problem. As Joost has said, the performance numbers are not like very far. You saw the numbers that he gave earlier, and they're fine. There's not going to be a real problem in terms of processing these algorithms. But where things kind of do get affected, it's not performance, obviously, as I'm saying, but it is in terms of artifact sizes. When you look at these artifact sizes, they're fairly large, right? When you compare them to something like ECC, for example, ECC, we're talking double-digit byte sizes for things like the public key, and things that go over the wire. In terms of these algorithms, the smallest public key is 800 bytes, and then the largest one is 1,568. So we're looking at like on the order of kilobyte size artifacts going over the wire. Same with ciphertext. So in MLChem, the ciphertext, the public key goes over the wire, and then the ciphertext comes back. So that's adding, approximately 2 to 3 kilobytes to the handshake. If you're on, gigabit Ethernet, this isn't a problem for you. But if you're looking at like, transmission mediums where you're going at like good old 1990s 9600K baud modem speeds, or if you're communicating with a satellite where um, you might have retransmission issues. This can affect things. Even more so for MLDSA, right? So these artifact sizes are even a little bit larger. So the public key goes out. Typically in this connection, there's a public key that gets transmitted, and then two signatures that go back and forth. So sorry, a certificate that gets transmitted has a signature and a public key embedded inside it. And then in the certificate verify message, there's another signature. So we're talking on the order of many kilobytes being added to the handshake. So this is where your end user might feel something. Also, in terms of memory usage, if you're on a constrained device, this might be rather concerning because these artifact sizes also require more memory to hold them. So, it can have an effect on your cost in terms of needing more memory and needing more processor RAM. Okay, so that brings us to the end of the presentation. I'll kick it back to Emma for Q&A.
Yes, wonderful. We have quite a few questions. So thank you, Anthony and Jim and Yost. We're going to dive right in. I believe this first question is for Yost. Do you support wolfSSL on NXP IWS 610 and IWS 612?
Actually, I think that one's for us, and
Oh,
I
yeah.
am not exactly sure about those particular parts. So I would have to go back and do some research. I think I can get back to you via email on that one.
Wonderful. All right, then this next one is for Yost. When will the IMX94 dev kit be available?
Yeah, thanks, Emma. That's a good question. So I know we have an IMX95 EDK currently available through one of our partners. For IMX94, I'm not exactly sure about the timeline, but we can definitely follow up on that to see what we can make available and in which time frame exactly.
Perfect. I kind of feel like Anthony or Jim could answer this question. What would be the performance numbers key generation signing verification for ECDSA and ECDHE we use today? Wanted to compare, if any, with the numbers presented for MLDSA, MLChem, and TLS 1.3 hybrid.
I'm gonna take that one. So compared to so it's different for every platform, but if we're looking at something like x86, generally speaking, ECDHE MLChem is far faster than MLDSA, or sorry, MLChem is far faster than ECDHE, and MLDSA is on the same order of magnitude as ECDSA. It's a little slower, but it's not something that you'll really notice in terms of performance issues.
Wonderful. Yost, this one's for you. Which encryption/decryption data rate can I expect on the IMX 93?
Yeah, also a very good question, and not a very easy question to answer on the spot because the data rate is going to depend on the specific platform. So I don't have a throughput number I can share with you immediately. So what I can say is that the IMX93 and also the rest of the IMX9 series include hardware support for AES inside the enclave. And so the data encryption and decryption rates are typically quite fast, especially as the message size increases. So it depends a bit on the use case. Yeah, we definitely have hardware support included in all of the IMX9 series to help with the AES performance as well. So yeah, that's why in the TLS session and in this proof of concept, we really focus on the asymmetric encryption layer or key exchange layer, because the AES is typically relatively fast in comparison.
Wonderful. This next one's for you as well. Can you speak to side channel countermeasures in the PQC hardware, NXP ELS, present and planned? And then what are the expected performance gains with, oh, I'm not quite sure how to pronounce that. KIAC hardware acceleration?
Jack, probably.
Jack hardware acceleration. Yeah, so that's a good question. So yeah, NXP has a big portfolio, right? So the amount of care for side channel protection depends a bit. We have secure elements, we have microprocessors, and we have microcontrollers, and the security targets and certification targets differ between them. So we are looking at all of them. And depending on the specific application domain or specific security target, the side channel and also fault countermeasures can change a bit. So for IMX9 specifically, side channel countermeasures are definitely considered, and also fault countermeasures are considered, especially in use cases like secure boot, where these are quite relevant. For Ketchak, so here, one very interesting kind of open source piece of material to look at is PQM4, if you're not familiar with it yet. So they track software implementations on the Cortex-M4, and they measure also how much time is actually spent in software in the SHA-3. And so I think for MLChem, it's roughly like 60% to 80%. And for MLDSA, I think it's even higher. It's like 80 to 90% is spent in the software hashing. So for our implementations, we don't know until we've done the integration and then measured it. But that's kind of the rough ballpark impact you can expect by integrating SHA-3 hardware in software on a core that's similar to a Cortex-M4.
Wonderful. This next one, they have an IMX93 board under development and would like to run up your POC. They see the code and attach like the GitHub link. Have you got this integrated into Yocto yet?
Are they talking about the POC has not been implemented yet? We're still in the midst of doing it. This is just sort of like a preview and a conversation starter as to how as to what's going on. But I believe that the GitHub link that led to the EdgeLock, the ELE GitHub repo, that I believe that does build on Yocto.
Wonderful.
Maybe to add, Emma, so I think there are different pieces to the POC, right? So it depends a bit. I think the NXP piece currently is not available yet publicly. So there is this public repository that we're building on, but the PQC part is not currently released yet. Currently, there's no plan to make the POC itself available directly publicly. But of course, we're looking at enabling ELE support for post-quantum crypto algorithms in general for the IMX9 series. And so this is something we're definitely looking into making available.
Wonderful. I feel like this one is kind of along the similar lines. These PQC HSMs are integrated into NXP IMX9 series or connected separately on the SoC.
Oh, I didn't quite get that. Can you repeat that?
Yeah. These PQC HSMs are integrated into NXP IMX9 or connected separately on SoC.
Oh, so the HSM is not part of the IMX9 series. Like they're separate things. So Jim, did you want to the HSM is kind of shall we say it's a kind of rack mount device, and it's completely separate. As Jim had alluded to, it's actually installed at the NCCOE offices, and it once it generates the artifacts, and it will get kind of like, you might say, email. It will be deployed to me by email, and then I will get it into the IMX 93 via
Yeah,
transfer.
yeah. Just to add to what Anthony said, given the configuration we're going to use, where the HSM is going to handle the generation of the provisioning, once we have that, we'll wrap it and we'll send it. Anthony and I will basically set up a secure transfer where I will send that provisioning blob to Anthony, and then he can use that to program the part itself. But yes, the HSM is typically it's an infrastructure component in most systems. You can embed HSMs into some systems. That's entirely doable. There are form factors that support that. But given the devices we're using, those are intended to be used in kind of an infrastructure kind of component where basically they live in a data center. Typically, there's physical protections around access to that device and everything. So that's kind of the use case that we're going for in this one.
Wonderful. Anthony, I believe this question is for you. Are open source stacks available only for the IMX or also the MCX and 947?
Yeah, so wolfSSL, all the things that you, so on the slide where I alluded to the history of our support, um, all of those are either bare metal or run Linux or run some sort of RTOS, and we support all of those. So if you have a particular part in mind and you're trying to figure out, does wolfSSL support that part? Well, the most important thing to know is what runtime you're using. Like if you're on bare metal, then you kind of have to figure out how to build wolfSSL on that bare metal environment, or if you're on the RTOS, or if you're on, Yocto. And we support all of that. So if you're trying to figure that out and you're having issues, you can always email me at support@wolfssl.com. So support@wolfssl.com, and we'll get you squared away and started.
Perfect. These next two are for you as well, Anthony. What are the licensing issues in relation to using wolfSSL, and will you have support for OpenSSL?
Oh, okay, that's interesting. So licensing wise, we have two licensing models. One is the GPL, and the other is commercial. So if you can tolerate the conditions given by GPL, if you're an academic trying to do experiments, for example, you're free to use us under GPL. You can find us on GitHub as well as our download page on wolfssl.com. Um, but if you can't tolerate the conditions given by the GPL, you can contact us at licensing@wolfssl.com, or even facts@wolfssl.com, and we can get you in touch with your with the wolfSSL business director that can handle your region. We handle licensing requests from all over the world, and so we'll be able to help you there. In terms of OpenSSL, yeah, we have great OpenSSL kind of compatibility. We have three ways of doing that. We have our OpenSSL build compatibility layer, and that's just a configuration flag that you pass in when you build wolfSSL. But we also have what's called the Wolf Engine and the Wolf Provider. If you're using OpenSSL 1.x.y, so anything with a 1 in front of it, then you can use our wolfSSL engine. And if you're using OpenSSL 3.x.y, so any OpenSSL 3 version, you'll be using Wolf Provider. And all of those are available on GitHub as well as our download page. And all of those are also available under GPL as well as commercial licensing terms.
Wonderful. Thank you, Anthony. We do still have quite a few questions. Are you guys okay to go over on time?
I'm fine.
Absolutely. Happy to speak as long as you're willing to put up with us.
Perfect. All right. This next question is for Yoast. Since EdgeLock is intended to provide the root of trust, key storage, and cryptographic operations, do TEE and EdgeLock expose a secure and efficient interface API that allows the TEE to leverage EdgeLock's capabilities? And then additionally, are EdgeLock's cryptographic operations backed by dedicated hardware accelerators or crypto processors?
Yeah, good question. So yes, absolutely. So the interface to the ELE is available from the application side. This works with or without trust zone or TEE. So definitely, if you're using a TEE, you can leverage that with the EdgeLock enclave. So the enclave currently, it depends on the product. So for 93, it is essentially a software implementation. For our future generations, we're adding SHA-3 hardware, which, as I kind of mentioned before, is really the bottleneck for many of these operations. And so for now, performance isn't too much of a concern. But depending on the requirements and the kind of how we see PQC develop over the next few years, of course, we are definitely keeping also hardware acceleration in mind as an option to provide any performance requirements that we might see.
Wonderful. Next question is for Anthony. Is wolfSSL the only open source that has been testing? In parentheses, does OpenSSL work? Is the linkage between the SSL/TLS stack via PKCS11?
So as far as I know, this project only involves wolfSSL, Crypto4A, and NXP. So there is no OpenSSL component to this demo. And the connection the API for wolfcrypt, where all the implementations are, is not a PKCS11 API. It is our own custom wolfcrypt API that wolfSSL calls into. So it is not a PKCS11 API. That said, we do have a wolf PKCS11 product where which builds on top of wolfSSL and does support a PKCS11 interface. So if you have a PKCS11 consumer, you can use wolfSSL underneath that PKCS11 consumer. Wolf PKCS11 is again available via GitHub as well as our download page.
Wonderful. The next question is for Yoast. Are there any plans to extend PQC support to the MCX N947 MCU family?
So for the latest updates on PQC support for NXP products, I would refer to the website. So we have nxp.com/PQC, where we have an overview of the NXP PQC strategy and also listing the products that are currently listed there. As you can imagine, we're not allowed to announce any products until they're cleared, also with marketing and management team. So really, all the ones that I'm going to mention are the ones that are listed on the website there. But please keep an eye out for any future platforms. There's definitely work ongoing to also support PQC on some of our other series.
I will add a shameless plug here. In November, we're going to be doing a joint webinar with NXP where we do show our post-quantum algorithms running on an MCX N947. And it'll be an interesting one. It's just going to show the main the main focus of that demo is to show TLS 1.3 with post-quantum algorithms running and communicating with a PC over Ethernet.
Wonderful. I believe this question came about during Jim's section, but how are these algorithms planned without the existing of a quantum computer yet?
Yeah, thank you very much, Emma. I saw that question. It wasn't clear exactly what the context was, but if the assumption is how do we ensure these PQC algorithms aren't going to be susceptible to quantum computers? Typically, what we do is when we're considering submissions to the NIST PQC process, and this is what people did essentially, you look at hard underlying number theoretic problems that we don't currently know have any kind of vulnerability to a quantum computer and its computational methods. For example, the reason that RSA is vulnerable is because Shor came up with an algorithm that allows you to essentially to factor large numbers efficiently. Okay, so that takes that off the table. ECDSA fails because there's a reducibility between factoring and computing discrete logs over elliptic curve fields and stuff. But when you look at the schemes that are being proposed, that things based on lattices, things based on codes, things based on stateless hash-based signatures and likes, at this point in time, we don't know of any particular advantages to running quantum computing algorithms to try and attack those. So, as a sense, we trust that those are going to be resilient. That being said, as was alluded to during the talk, given that we're already making some changes, we're not just going to put all our eggs in one basket. So what we're typically going to do is we're going to use hybrid techniques where we actually use multiple algorithms to protect things, such that if we were able to find an efficient break of one of them, the other one can still step in and provide that security. And then furthermore, if we use the crypto agility notion, we're going to make it so that we can quickly transition off of, say, those two algorithms where one's broken to the one that isn't broken plus another new algorithm. So we're going to have this ability to evolve over time and to change the protocols, to change the algorithms so that we can try to stay one step ahead of the attacker essentially, and not have this kind of situation again where all of a sudden we're panicking trying to change an entire cryptographic infrastructure to get off of algorithms that are no longer secure.
Thank you. Yoast, has the IMX93 platform addressed the T memory limitations that prevent PQC operations? Specifically, our tests show OPTI 4.4 on the IMX93 EVK cannot support even a single dilithium 3 operation due to the 73 kilobyte memory constraints. Have there been any firmware updates, architectural changes, or configuration options introduced to enable proper PQC support in the T?
Yeah, good question. So here I would say, so one of the main challenges we have been working on, or maybe one of the first challenges we've been working on for PQC, maybe starting 2021, 2022, was how do we make PQC run on embedded systems? You know, these initial implementations from academics or from the submission teams, or even in PQM4, indeed, they had very large RAM requirements, meaning 70K, but even more than 100 kilobytes to simply sign something or simply verify something. So we spent quite some effort, some years back reducing this. We also published this. We have a paper at Africa Crypt where we really minimized the work area or the RAM required to verify or sign something using MLDSA. And we have also other investigations for other algorithms, for example, FrodoChem. And so you can really reduce this 70K or 73K that you mentioned in the question here. I think we reduced it down to even 4 kilobytes for dilithium signature generation and only a few kilobytes for signature verification. So this can definitely be reduced, and this is really necessary to enable them for TEs. And also it's really necessary to integrate them into secure elements, secure enclaves, which typically have very limited RAM to work with. So I would also say if you're using the enclave together with your TE, then of course the actual RAM requirements are not on the TE. Right? The full operation is done inside the enclave. So any keys are stored in the enclave. Any RAM that's required for the operation itself is also done internally as part of the enclave. So you wouldn't need to allocate anything on the TE side. So I think those are the two options. You can use the ELE. This will reduce the RAM requirements immediately, and if not, you can try to use a library that has a much lower RAM requirements than 70K, which are available now.
Wonderful. This question is kind of similar. Is there or will there be U-boot support for the IMX9 Secure Enclave, including for the PQC algorithms?
Yeah, so yeah, that's not my area of expertise to promise. So I think any use case where secure boot or PQC is relevant, we are definitely looking at integrating it. But I don't know what the timelines are for U-boot and if this specific use case is targeted and what priority it has. So I would imagine yes, this is definitely a very important use case, but I wouldn't be able to say exactly when and how we would be supporting that. But we can definitely follow up on that if you maybe easiest if you simply reach out with an email and I can connect you with the right people who can comment on that.
Wonderful. This one kind of goes hand in hand again. What kind of difficulties have you faced while implementing those features?
Pausing if you want to take this question, Jim, or
I think he's referring specifically to on the I.
oh, okay. Yeah, I
I-
mean, then I would say kind of roughly what I said before. Right? I think memory is a very big challenge. So getting things to run on embedded platforms was a big challenge. I think by now we've solved many of those challenges. The next challenge is maybe looking more at side channel protection, fault protection, high assurance certification. Also dealing with certification labs. I think certification labs also have to get up and running to be able to certify these implementations. We've seen a lot of papers come out in recent years, at chess and other conferences where they're focusing on, doing side channel attacks on post-quantum algorithms and doing fault attacks on post-quantum algorithms. And I really I think that's a great development. I would really urge anybody that's interested in that to work on that, so that we can kind of catch up the maturity of attacks of post-quantum algorithms on the level that RSA and ECC are today, which will increase the confidence in these implementations even further. But I think this will take some years. And then especially for the algorithms that are still under development in the on-ramp and maybe even HQC and Falcon, I would mention.
Perfect. Joost, what could be the strategies to handle these large artifacts, say on the IMX9 SoCs or just in general in a constrained device? I also have a question about performance numbers above. I think we already answered that.
So I'm not sure exactly what large artifacts you're referring to here. I imagine you're referring to large key sizes or large ciphertext or signature sizes. So yeah, it depends. I think for some use cases, it's really hard. Right? Some protocols just mandate the use of certain signatures, and then there's little way around it. For some cases, we're seeing that you can change the architecture of the system a little bit and really reduce the storage required from public keys, especially. So instead of storing a public key, for example, it's typically a good idea to store a public key digest, so storing only a small fingerprint of the public key, and then supplying the public key at runtime, for example. So that means you don't have to have the physical storage of the full public key or even of many public keys, but only have a fingerprint that you then check at runtime. So this helps a lot. These are typical strategies to also reduce the size of the root of trust, where memory is typically very valuable, especially for fuses. So strategies like that can help to reduce the cost on constrained devices. But indeed, for some cases, yeah, signatures are larger, keys are larger, so sometimes there's just not so much you can do. But we try to minimize the impact as much as possible.
Perfect. I hope you have some water. There's quite a few questions for you. And here's another one. Are you assuming the HSM is in the embedded system itself? Typically, you'd see more of the secure enclave elements like EdgeLock that Joost has mentioned showing up in the network itself. General purpose HSMs would be found in the infrastructure supporting manufacturing and any live operational networks providing cryptographic services as an on-need basis. Those HSM elements will be able to provide any required security mechanisms through though typically they don't use MACsec, but rather IPsec or TLS for securing their external communication links. The underlying network and switching infrastructure might utilize MACsec, though.
Yeah, actually, Emma, this was a response that I wrote to Gertup
Oh,
in response
okay.
to another one of his questions, and he submitted it into the QA. I suspect it was just a copy paste error. But yeah,
Okay.
Gertup's original question was whether or not you would see an HSM essentially in an automotive system. And I was just responding to him that typically the HSM itself doesn't get embedded into the car, although they do have things like in like small form factor like secure enclaves and likes, which would be sprinkled throughout the automotive network. But typically the HSM would live off in some kind of support infrastructure, like a data center that has network connectivity to a device that it could be signing things for it or providing provisioning information or being used in the manufacturing process of the elements that go into that kind of automotive environment. So that's what I was trying to convey to him. And he was also asking about MACsec and IPsec and whether or not that'd be supported. Typically, an HSM is not going to support MACsec. That's kind of a layer 2 protocol. It's more a switching kind of thing in the network infrastructure. But it would definitely support, like we support IPsec and for VPN tunneling and the likes. We support TLS for talking to external clients and the likes. So those kinds of interfaces are absolutely supported by an HSM, but typically not a MACsec kind of thing. That's usually a little too low level from the perspective of an HSM. It's more a high level application.
I'd like to
Maybe.
add to.
Oh,
Oh,
No,
sorry.
go
I'd like
ahead,
to
Anthony.
Jim.
Go ahead. Go ahead. You go ahead.
Oh, sorry. I'd like to add to Jim's answer that perhaps the question was talking about embedded HSMs, and
yeah.
wolfSSL's newest product, Wolf HSM, is tailored to that use case. So if you want to look up Wolf HSM, you might be interested in that. Go ahead, Yost.
No, thanks, Anthony. I was going to say something very similar. I think, especially in the automotive domain, the term HSM is also a bit overloaded. So, I
Yeah.
mean, often an enclave or an onboard ELE like is referred to as an HSM, right? So you have to be a little careful. When somebody's talking about an HSM, does that mean the HSM on the SoC or the one that's in the infrastructure, right? And that can change whatever it's doing.
Wonderful. Thank you guys. Can the ARM Cortex-M also be seamlessly integrated with PQC algorithms?
I'll take this one, Emma. And the answer is, of course, yes. wolfSSL already has, even some already supports ARM Cortex-M. We even have ARM assembly optimizations for the PQC algorithms, MLChem and MLDSA. So go ahead and download our code and turn on the assembly optimizations when you're building, and you should see quite the performance improvement.
Perfect. Is a Yocto project layer available to implement these features?
I'm not sure who this question is for, but yes, wolfSSL does build on Yocto. So go ahead and download us, and we even have videos on YouTube where we do webinars telling you how to build. I believe there's shorts actually. If you look in our YouTube channel and check the shorts section, we have shorts on how to build for Yocto. Yost, I don't know if you want to speak to Yocto and the IMX93.
Yeah, I mean that there is integration into Yocto for sure. Yeah, the PQC support is currently not supported in any of those layers yet, right? But indeed, we have a lot of support for Yocto as well as part of the IMX9 enablement.
Perfect. Is there a level of security for common criteria for embedded HSE in CPU, like S32G2 or 3, level 5 plus 5 or more?
Yeah, that's a question for me, I think. So the HSE, so the S32G2 is an automotive processor from NXP. So it has an EdgeLock Enclave, which is not called an EdgeLock Enclave in that case. It's called a hardware security engine. That's the HSE. So this is not common criteria certified currently, right? So it definitely provides the security guarantees that I mentioned also about the EdgeLock Secure Enclave. It's a physically isolated, dedicated core with with more protection than the application domain, but it's not reaching the security levels that a common criteria certified secure element would, for example.
Actually, a
Wonderful.
question for you, Yost. Is it the case that is there a protection profile defined for these high security elements, for these embedded in an SoC? Does that exist in requirement criteria?
I'm not sure. So this is not something NXP is currently doing. So I'm not sure if that means it doesn't exist or whether we are just not following it. I don't believe it exists, but yeah, don't quote me on that. Maybe.
Okay.
Perfect. I believe these next questions are for Anthony. Can we have the PQC libs run on the Cortex-M series for a similar use case? And then can TLS 1.3 only use a part of PQC, say just MLDSA and or MLChem?
Okay, so for the first question, yes, the answer is yes. I think I alluded to this already. You can even turn on the assembly optimizations for ARM, and it'll work. So you can have software implementations from wolfSSL. In terms of TLS 1.3, the answer again is yes. So MLDSA is MLDSA is the authentication authentication portion of the TLS handshake. And so as long as you're using MLDSA certificates, then you'll be using MLDSA authentication, MLDSA signature scheme in the authentication half. MLChem needs to be specified within the groups and the key share. But yeah, you could only have MLChem in the key share and then use ECC ECDSA for the authentication algorithm. And a lot of people do this right now. This particularly addresses the use case for harvest now, decrypt later. So your key establishment is quantum safe, but your authentication would be still with ECC.
Wonderful. Can you specify the difference between GPL v2 and GPL v3, Anthony?
I will not go into the differences, but I will let you know that wolfSSL is now GPL v3. If I were to speak to the differences between GPL v2 and v3, that would constitute legal advice. And I can tell you, I am definitely not qualified to give legal advice. But I can tell you that wolfSSL is now GPL v3.
Perfect. Is there a full TLS 1.3 support on the IMX RT MCU, like the IMX RT 1060, for example?
Yeah, I would have to double check. And maybe that's more a question for you also, Anthony. I think the interface we support there is the same we support on the IMX 93, right? So we provide application level support for ECDH interfaces as well as a TLS 1.3 key schedule. And yeah, similar to what we presented here, that any kind of higher level TLS stack will have to be built on top of that.
Yeah, so if you build wolfSSL for the IMX, for any of the IMX devices that we support, and we support basically all of them, you can just you don't even need to use a flag. TLS 1.3 is enabled by default. So yeah, you can do that.
Perfect. Can you list some of the secure element which we can use for the PQC and also the controllers?
Is that to me? I'm guessing that's to
Maybe
me.
to Yoast.
Yeah.
Is this like industry wide? We're looking for a list.
Yeah, I imagine it's referring to NXP. So, I mean, currently for NXP, we're working also on proof of concept for our secure elements. So, like none of the product portfolio has integrated support for post-quantum yet. So yeah, this is something we're working on. I mean, if you're interested in more details, yeah, please reach out and we can see what we can share. But similar to what we're doing for IMX 93, we're mainly working on proof of concepts for some of our existing portfolio.
Wonderful. And final question, is Optica Trust M-chip compatible for the PQ?
Optica Trust. Is that an NXP product?
That is not. I believe that is an Infineon product, if I'm not mistaken. So I'm not.
Yes,
I'm
it is
not-
Infineon.
So if it's an Infineon product, and again, if that's a microcontroller, which I'm not sure, but I'm not familiar with the product. But I will tell you right now that if it is a microcontroller and it has a SDK with a C compiler, we will get it. We will get it going, no problem at all. So do reach out to us. You can ask you can contact us at fax@wolfSSL.com, and I promise you we will get you going.
Wonderful. Well, thank you, Anthony, Jim, and Yost for hosting an informative webinar. Thank you to everyone for joining. You can keep up with our upcoming events, meet our team in person, read our blog posts, and get the latest wolfSSL updates by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have any more questions, please reach out to us at fax@wolfssl.com. Thank you again, and we look forward to seeing you on September 24th for our webinar on achieving avionics security with DO178C certified cryptography. Thank you all.